Yesterday's quiz question was you were asked to draw all the isomers and to name all the isomers of a molecule with the formula C5H10. So all the isomers drawn in bond line notation is probably the most efficient way of doing it, because with bond line notation you don't have to draw in all the hydrogen. Suffice it to say that as long as you draw molecules with 5 elbows or 5 terminal groups, in other words 1, 2, 3, 4, 5, you will have 10 hydrogens present. Why do we go through the trouble of finding the index of hydrogen deficiency? Because it helps us to zero in on whether the molecule has a double bond, a ring, or whatever. Every time you're missing 2 hydrogens from the formula as compared to the saturated alkane, then you know you have at least a ring or a double bond. Because whenever you join 2 ends of a molecule to form a ring, you have to sacrifice the bonding of 2 hydrogens to do that. And likewise, when you have a double bond, that double bond takes away the place for 2 hydrogens. So once we've established that the molecule has to have a ring or a double bond, not and or, once we've established that the molecule has to have either a ring or a double bond, we proceed logically to list all the different possibilities. So the first and most logical possibility is that you have cyclopentane. Then we proceed to molecules that have 4 carbons in the ring, which leaves us 1 extra carbon as a methyl group to put on there. And no matter where you put it, that's the first position. We don't even have to put the substituent 1. So it's called methyl cyclobutane. Then we proceed to a 3-membered ring, which leaves us the possibility of 2 extra carbons. So the first logical possibility is to call it ethyl cyclopropane. Then we can also place those extra 2 carbons as 2 methyl groups at the same position. That would be called 1,1-dimethyl cyclopropane, or we can put them 1,2. So we get 1,2-dimethyl cyclopropane. If you put it at the 3rd position, it's still called 1,2, because wherever you put the second substituent is the second position. That exhausts all the ring possibilities. So now we proceed to list all the isomers that have a double bond in them. The first logical alternative is pentene. 5-carbon chain, double bond at the first position. Then we can slide it down to the second position, which gives rise to the possibility of cis-trans isomerism. So we can get trans-2-pentene or cis-2-pentene. Then we have, that exhausts all the possibilities for pentene, because if we put the double bond at what we think is the 3rd position, it's actually the 2nd position, because then you would number it from the other side. So you can't have 3-pentene, it's called 2-pentene. So we go down to butenes now, and we start with our double bond at the first position. That leaves us 1 carbon, so we put a methyl group at the 2nd position. If we were to put it at the first position, we'd be back to pentene, so that's not possible. 2-methylpentene. Then we could also take that methyl group and put it at the 3rd position, giving us 3-methylbutene. And the last possibility is to move the double bond to the 2nd position and putting the methyl group at the 2nd position as well. If we try to put it at the 3rd position, it's still the 2nd position. So we get 2-methyl-2-butene. There are only 11 isomers for the formula C5H10. As a challenge, you can try to draw all the isomers for C6H12. There are 29 isomers with that formula, and I've also posted that video on this website. Carboxylic acids. This section of the homework comes from Pine, Hendrickson, Cram, and Hammond, a very good textbook that I used when I was in college. The nomenclature of carboxylic acid groups is typically given the suffix oic acid. So whenever you have a carboxylic acid attached to a straight chain alkane, you end it with oic acid. If the carboxylic acid is on a ring, you say carboxylic acid at the end of the name. If the carboxylic acid is a substituent, which occurs fairly rarely, since carboxylic acids have near to the highest priority, then you use the prefix carboxy. So here are a few examples. We have this molecule drawn in bond line notation. It's 5-carbon chain in length with a methyl group at the 4th position, so we call it 4-methylpentanoic acid. See the suffix oic acid. If you have the carboxylic acid on a ring, you say benzene, ending with carboxylic acid. This is also known as the trivial name for it is benzoic acid. Much more common usage is to use the trivial name. In this molecule, we have a mixture. We have a molecule that has more than one functional group in it. We have a ketone and a carboxylic acid. Ketones are of lower priority, so we start the numbering from the position where the carboxylic acid group is, and we give it the oxo designation when the ketone is a substituent. So this molecule is 6 carbon chain in length, with the 2 methyl groups at the 5th position, so we call it 5,5-dimethyl 3-oxo-hexanoic acid. Then there are a few examples in the questions. Actually, there's one more example here with a heptene. The longest chain here is 7. There's a double bond at the 5th position. There's an amino group at the 3rd position. Remember, when there's an amino group as a substituent, meaning there's something of a higher priority within the same molecule, then you use the prefix amino to name it. If the amino was the only group in there, then you would call this an amine. So we call this, numbering it from the position where the carboxylic acid is, 3-amino-5-hepten. The En is to signify the double bond. Heptenoic acid. This molecule is also a carboxylic acid. It's 223 on the exercise sheet. There's a methyl at the 2nd position, a phenyl group at the 3rd position, and its longest chain is 5, so we call it 2-methyl 3-phenyl pentanoic acid. Here's the acid part. This one has 2 carboxylic acids on the same molecule, so it's going to have dioic acid, and there's a chlorine at the 2nd position, so 2-chloroputane dioic acid, butane dioic acid. Drop the E. C has a carboxylic acid on the cyclopentane ring. So 3 separate words: cyclopentane, carboxylic acid. Whenever you have a carboxylic acid on a ring, you use this technique to name it. This one, you'd be tempted to call it cyclopropane carboxylic acid, but there's an intervening carbon there, so we're going to name it as a substituted ethanoic acid. So it's 2-cyclopropyl ethanoic acid. Ethanoic acid also has a trivial name. It's acetic acid. That's the more common usage. So you could also call it 2-cyclopropyl acetic acid. This one is a